Thank you, Chairman, and good afternoon, everybody. I'm going to talk today about the issue of end use, and let me start initially with a brief definition. Essentially, the issue here is that we're looking at the control potential of electrical and thermal loads used in commercial, domestic, and industrial applications as a demand management and reserve provision measure. Now, the work that we're doing at the moment is primarily focusing on the commercial sector and the domestic sector. And the other point that's made there, we're looking at electrical loads, but also thermal loads. Now, when I say thermal loads, I mean thermal loads that are driven electrically. So I'm considering things like ventilation, air conditioning, heat pumps, and other thermal loads that are generated by an electrical driver as such. Let me briefly introduce the people. Along with myself, also involved in this strand is Damien Flynn, and my colleague in mechanical engineering, Simos Oxidas. And then there are 4 PhD students actively engaged in this strand. Most of the work in this strand is quite recent. All of the PhD students have joined us within the last 12 to 15 months, and some of them indeed have just started in the last 3 to 4 months. The bigger question or the context, looking at my earlier definition there of what I mean by end use, it's the context of, and it's something which we've heard already, is the decreasing use into the future of fossil fuels and the generation of electricity here in Ireland, and the increased use of renewable sources. In that context, the demand and demand-side response is a measure that is certainly worth looking at, and is what's driving our work here. And in particular, our focus, as I mentioned earlier, is on the residential, domestic sector, and also the buildings commercial sector. At the moment, we don't have activity focused on the industrial application sector, but that may change in time. Looking at then what are the change perspectives, essentially it's driven by a mismatch between the supply and demand perspectives. Balancing large-scale generation against a variable demand profile is the first issue, and secondly, we have the increased contribution from wind generation and its variability. And then against that, there's ongoing developments in communications, in building energy management systems. We have the imminent rollout of smart metering, the development of home area networks in domestic buildings, and then the likelihood of time of use or real-time electricity pricing, not happening at the moment in Ireland, we say at a domestic or commercial level, but happening in some other markets. And I guess the past assumption of a largely uncontrollable load, that's the demand side, is something that's going to change. And on top of that, then, you also have an increased penetration of renewables, which means there's demands from a system flexibility perspective. It's worth for a moment just standing back to look at the issue, what do we mean by demand side management and demand side response. And this perspective here, this is taken from Linda Hull, who works with EA Technology in the UK. She gave a presentation or a talk at a recent workshop that we had here in Dublin at EirGrid in November. And this perspective, I think, is quite good. Now, it may not be necessarily the perspective that everybody views, and I guess this is more from perhaps the perspective of government or from someone like the, let's say, SEAI. But what you can see here is there's 4 key components. There's what's called permanent change, efficiency measures, local and renewable generation, and flexible loads. A few points here. First of all, you see these different perspectives overlap each other, so they're not mutually exclusive. If you think about permanent change, it's really systems change. It's possibly, or it is the gradual electrification of the grid, and particularly electrification of loads on the grid. So perhaps the move from fossil fuel heating of domestic buildings towards electric heating using heat pumps. That would be one example of that. Energy efficiency measures. Here on the right-hand side, there's relatively straightforward efficiency improvements, like, let's say, moving from conventional lighting to LED or CFL. But then there's also more sophisticated, another example as well would be, say, let's say, more efficient motors used in pumps and fans. But then there's also more sophisticated energy efficient measures, which is to do with integrated control of the energy systems and buildings. And I'm not going to talk about this today, but our research group are involved in a number of FP7 projects which are looking at the integrated control of heat pumps with buildings. And in this case, we're looking at optimization, dynamic optimization of the systems, integrating both the building, the heat pump, and all the integral components. So it's taking a more holistic perspective. Over on the left-hand side, we have local and renewable generation, which is another part of demand-side management, where you have local generation. And primarily today, I'm going to talk about the last part, which is demand-side response. So this is looking at dynamic load management, in this case in buildings, commercial and domestic. So some perspectives on demand-side response, the measures that are available to you. There's peak clipping, which is the first in the top left, is the reduction of load during peak demand times. Valley filling is basically improving the overall utilization or load factor by load building in times of lesser demand. Conservation, we saw earlier, falls into the efficiency measures. Flexible load shaping is basically reshaping the demand using interruptible or curtailable agreements. And then load building and load shifting. Load building is relevant in the context that if you have too much wind generated power, can you absorb that in some way by the demand? And finally, load shifting is basically shifting peak load to off-peak times. Within this then, there are various incentives available, which are either price-based or more holistic or incentive-based. And we can see here, looking at this perspective, as you go from left to right, there's a time-based element here. So looking at here at energy efficiency measures, you're looking at something that's more over years, gradual, slow improvement. And as you move here towards the extreme right, you're looking at quite immediate measures that we saw in some of the earlier talks today. Looking at price-based demand response programs, you can have time of use rates, which are applicable usually over longer periods, and then you have day-ahead or real-time pricing. And then on the bottom side, looking at incentive-based programs, there's a range of different packages that are potentially available as well. So that is the framework within which we're working and within which we're doing our research. So this brings me then to the research strand and the actual research work that's going on. So as I said earlier, there's 4 PhD students. So what I'm going to do now for the remainder of my talk is to briefly introduce the objectives of each of the individual research projects that the students are doing. I'll describe 2 of them in a little more detail. They're the projects that started just over a year ago. All of the students have posters available, so if there's any particular project that you're interested in, make sure to take the opportunity to speak with the students. So the context, as I said earlier, we're focusing at the moment on demand response measures in buildings, particularly in domestic and commercial buildings. So our first student, he's a graduate of our ME Energy Systems program. In this case, Olivier, he's looking at the assessment of demand response potential of electrical loads in Irish residential stock. So it's looking at the potential of all electrical loads in the entire stock nationally. The other 2 students then, Despina and Fabiano, both of them are working on the development of algorithms capable of being implemented in a demand response context or environment. So Despina is working on commercial buildings. Fabiano is working in the area of residential buildings. And finally, just joined us 2 months ago is Demetrius. His work has been funded by UTRC, United Technologies Research Corporation, and the Irish Research Council. And he's looking at the development of a methodology to assess the energy behaviour using reduced order modelling techniques and data mining techniques in buildings. I'll come back to talk about each of these in a little more detail now. So I'm going to start first of all with the work of Olivier. Looking at demand modulation of residential buildings. If you look at residential buildings, first of all, they occupy about 1/3 of the total electrical load. And here on the expanded part of this electrical load, we can see the breakdown in terms of the electrical consumption. And in this we can see there's space heating, hot water, cooking, refrigeration, wet appliances, so that's dishwashers and washing machines, and lighting in this case. So the fundamental question that Olivier is trying to answer is how much flexibility is embedded in electrical and thermal loads. And when I say thermal loads, I mean thermal loads that are driven electrically through the application of demand modulation strategies in Irish building stock. And the objectives is to identify or is to use archetype buildings representative of Irish households. Now, the approach that we've used to date is there was work done by the Energy Research Group here in UCD, where approximately 8 archetype buildings were identified for the Irish building stock. So the idea is to take these and to basically create a building energy model of this and use this to assess the energy demand within the building. And a more recent report, which was published just a few weeks ago by SEAI, has refined that down to 5 archetypal buildings. So it's something that's readily doable in this context. And the package that we're using for this is Energy Plus, which is a building energy simulation package. What this will lead us to is an assessment of the demand modulation capabilities in each archetype model. And then we've got to correlate from those 5 archetypes up to the grid perspective. This is an example of some results. This is one of the archetype buildings here. It's a bungalow. As you can well imagine, is a significant player within the Irish residential sector. And the approach that Olivier is taking is he's looking at he's analysing all of the electrical loads within the building. So here we can see, we say domestic hot water, looking at the water heating system, space heating system, the lighting and appliances. But critically what he's doing here is we're using a bottom-up approach where we're using a study from the ESRI, which was conducted in 2005, which was based on time of use data, where you get quite a good indication of the occupancy patterns and the usage and the activity patterns within dwellings. And this allows us then to analyse what's happening. So this shows some results. This is for a Monday to Friday sequence in September of 2009 in this case. Is the period that we use. The reason we're using this is there's also data available from the CER, from the smart meter trial. And this is shown in the red line here. So this is a 24-hour period, and this is the aggregated electrical load within a cluster of buildings that follow this archetype. 1 or 2 points here. There is a difference between the predicted results. So the predicted results are in green and blue. The main difference is that at this point, the domestic hot water requirement hasn't been modelled yet. So that is the main reason. But apart from that, the trends associated with the modelled results and the CER data track each other very well in this context. So when this is expected, or when this is completed, we would expect to basically bring the model data relatively close to the CER data. The next project is been undertaken by Fabiano Palonetto. It's looking at the development of demand response algorithms in domestic applications. So this is the sort of context here where we're looking at a home area network. It acts as a type of energy management system, and these are the different loads that we're looking at controlling. So the fundamental question here is, can demand algorithms be effectively developed and used in residential buildings in such a way that domestic buildings can act as a demand response mechanism. So the objective really is to, first of all, look at an all-electric building, because that's the type of future that's envisaged. And again, we're using a building energy simulation approach because we're taking a bottom-up approach in this context. The second objective then is to develop demand response algorithms and then to test and optimize in an actual building. So in this case, we're using this particular dwelling, which is a dwelling of a retired member of the Building Services Department here in UCD. He's made his house available to us for this. This is the specification of the thermal and electrical equipment, particularly the thermal equipment which is electrically driven in the building. This is the house before retrofit, so this house has been retrofitted over the last 12 months. So it was a pretty conventional building with space heating provided by oil and by wood, an immersion heater with solar thermal, and also a car which was a conventional 2-litre car. And the retrofit has moved to a ground source heat pump. The solar thermal and immersion was already there, so that's there as before. The additional of thermal storage, heat recovery, a PV system, and a Nissan Leaf EV in this case. And these are some preliminary studies which were done using the Energy Plus simulation package. What we're looking at here is a 24-hour period in the January-February period of 2010. We're looking at CO2 emissions for that period. And remember, we've got the baseline dwelling, and we also have the all-electric building. And there's two scenarios then. We've got a 20% wind penetration on the grid, and we have a 4% wind penetration on the grid. So what we're comparing is the all-electric or the retrofitted building with the baseline building under a high wind penetration scenario and then under a low wind penetration scenario. And what we can see here, first of all, the general trend is as you move towards a more all-electrification of the building, that you get a reduction in the CO2 footprint. And also, as you move towards a higher wind penetration, you also get a further reduction due to the lower CO2 footprint, which is associated with electricity production. The other two projects, because they're newer, I'm just going to give an overview of them. This is the work that Despina is working on. It's, in many ways, it's not dissimilar from the work of the home area or networks in the domestic building, except for we're looking at commercial buildings in this context. And what we can see here on the in the pie chart is the various energy consumption features which are typical of a building. Now, this is taken from the US Department of Energy, but we can see here that space conditioning, which is heating and cooling, which is quite common in large commercial buildings, is a significant part of the electrical load. And also, along with the other load types, you can see that we have these ones here, which are part of the sort of the central core. This is just simply noting the point that these loads are in some way controllable or deferrable from a demand response perspective. Whereas some of these other loads here, like computer usage, electronic equipment, is something that, from a demand response, is not readily available. So the objectives here, the research question is quite similar to the domestic buildings, except for we're looking at applying demand response algorithms to commercial buildings. And we want to investigate the automation capabilities in the context of commercial buildings for different demand response programs that we saw earlier. And then we're also using simulation models to analyze what's happening. We're particularly interested in seeing, apart from applying the demand response programs, is how does that affect the comfort within buildings from a thermal perspective? So how does it affect the perception of the occupants and also the CO2 levels within the buildings? Because that's a critical issue insofar as if you change the environment, you may be making some advantages from a demand response perspective, but you can also affect productivity in some way. And then the idea is to implement these on a commercial building. The commercial building that we're going to use is going to be a building right beside us here is the new UCD Sports Centre, which has a lot of commercial-like features, and we'll be collaborating quite closely with Cylon on that, and also with the UCD Building Services Office, or Buildings Office. The last piece of work, just very recently started, is been undertaken by Demetrius, and it's been sponsored by UTRC, who have a research office in Cork, and Irish Research Council. The question here is that when it comes to trying to understand the response of buildings to, we say, changes in weather that will happen tomorrow or will happen later in the day, or to different occupancy, using detailed simulation packages like Energy Plus or Transits, these are energy simulation packages that are used in the building energy analysis community, require significant investment to set them up and to model the building. And UTRC are interested in basically, can we develop what we call reduced order models, also called grey box models, which are basically a simplified approach that gives a reasonable prediction of behavior which can be used within something like a BMS system. So there's two traditional approaches. There's white box approaches. This is the full sort of scientific detailed approach. And then you have black box models, which are things like, we say, artificial neural networks, which is a data-driven approach. The idea of using reduced order model is you're basically using features of both, but the key issue is that they can be implemented on BMS systems, and that is a critical part to implement some of the demand response initiatives that we're thinking about. Finally, I've just put together this slide. This is taken from the CER Demand Side Vision report, which was published in 2011. I've selected out of this the parts which are relevant to the work that we're doing. Apart from energy efficiency, and really what we're looking at here is we're looking at the concept, the sector, the cost, and the ranking in terms of importance. I guess the point I want to make here ultimately is that we're essentially involved in all of these activities in terms of the home area network automation, in industrial and commercial DSR activities, and also in residential. So in the work that we're doing, we're in some way, we are addressing some of the issues that were highlighted in this report that are of high priority. So that brings me to the close of my presentation.